This is problem number 2 in chapter 22. And so this deals just with the energy associated with the photons of light. And so we use the equation relates energy to Planck's constant and the frequency. And that relationship is, if I can find it here, that energy is equal to H times F, where F is the frequency and H is Planck's constant, which is 6.63 times 10 to the minus 34 joules seconds. Again, this is called Planck's constant, after I think I named Ernst Planck. So, in this particular problem, we are told, what is the energy in joules of an X-ray photon with a wavelength? So the wavelength is 1.00 times 10 to the minus 10th meters. What we need to do to calculate energy is we need to find the frequency. So we have the second relationship that says that the speed of light is the product of the wavelength times the frequency. So given the wavelength, we can solve for the frequency, and it's going to be equal to the speed of light divided by the wavelength. And the speed of light is 3.00 times 10 to the 8 meters per second. And the wavelength is 1.00 times 10 to the minus 10th meters. So the frequency, and I think this is a fairly low wavelength. I don't know if it's infrared, ultraviolet. Anyways, 3 to the 8 divided by 1 e to the minus 10th, which is actually just going to be 3 to the 18th if you just using the exponential parts. 3 divided by 1 is 3, and 10 to the 8th divided by 10 to the 10th is 10 to the 18th. And this is hertz, cycles per second. Okay, so another page. So now we do have the frequency. And so the energy in joules, because this is joules per second. So we get Planck's frequency, well, Planck's constant in there. We get 6.63 times 10 to the minus 34th joules seconds multiplied by the frequency, which is 3.00 times 10 to the 18th hertz, which is hertz or cycles per second, so the seconds will cancel out. 6.63 e to the minus 34th times 3 e to the 18th. Apparently I have typed in something wrong. I think I used minus instead of negative. So we get 1.99 times 10 to the minus 15th joules. So we want to convert to electron volts. And all we have to do is we know that 1 electron volt is equal to something, and I think we have to go to the back of the book, or the front of the book. Must be the front of the book. Under energy, there'll be a conversion from electron volts to joules. So we have 1 electron volt equals 1.602 times 10 to the minus 19th joules. So since this is more than that, we're going to divide this by that so that we get some number that's more than 1 electron volt. So the energy in electron volts, we just take 1.99 times 10 to the minus 15th joules. And if we divide by 1.602 times 10 to the minus 19th joules per electron volt. So when we do that, we get 12,400 electron volts, which is pretty high. We did something in class the other day. I don't know if we're looking at light waves or yeah, I think it was light waves, and we found out it was a couple of electron volts. So because of the short wavelength and their high frequency, we knew this was going to be a higher energy photon. So every photon for this particular light wave will have this energy. Okay. Convert the energy to electron volts. If more penetrating X-rays are desired, should the wavelength be increased or decreased? So if you want more energy, then you should increase the frequency, which will decrease the wavelength. So more energy want to decrease the wavelength. One thing too is if you think about radio waves, those are pretty long, meters. And so those are really long, therefore the low energy. So really short wavelengths are high energy. And also we can look at it the way more energy means to increase the frequency. Since they're inversely related, the product of those two give you the speed of sound, speed of light, which is constant. Okay, let me just stop for a second, check the answer, and I'll let you know if everything's okay.
Recording started.
Okay, we're good to go.
Recording started.
Okay, we're on problem number 10. So let's read it. A beam of light traveling in air strikes the surface of mineral oil at an angle of 23.1 degrees with the normal to the surface. If the light travels 2.17 times 10 to the 18th meters per second in oil, what are the index of refraction of mineral oil and the angle of the refraction? So let's draw a surface. We have our light ray coming in, which has an angle of 23.1 degrees relative to the normal, which is perpendicular. So this angle here is, we'll call that theta 1. Theta 1 is equal to 23.1 degrees. Okay. The speed of light in air is basically the same as in a vacuum. So you have we'll call this C1, 3.0 times 10 to the 8 meters per second. And so then it says it travels, so C in the mineral oil is 2.17 times 10 to the 8 meters per second. So the ratio of the speed of light is the same as the ratio of the index of refraction. So we assume that N1 is equal to 1.0, which is air. So N2 is going to be greater. N is always greater than 1. And N of any object is either equal to or greater than 1. So from that we kind of can figure out which needs to go on top. So we need to put the speed in a vacuum divided by the slower speed, which is this. And because they're both times 10 to the 8, and also they're both meters per second, we just have to take 3 and divide by 2.17. You don't have to include all the extra stuff. 2.17. And we get 1.38, which sounds like a pretty reasonable number. Okay, so that's our index of refraction. Now, as far as what is the angle of refraction, well, because this material has an index of refraction less than 1, we don't want to come at this angle, we have to actually come towards. If we went straight, if they were the same material, it would just go straight through. But what happens is we have this thing bent, and it bends towards the normal. So theta 2 is less than theta 1. So that's theta 2. And Snell's law says that n1 sine of theta 1 equals n2 sine of theta 2. So let's just write that down. Snell's law. n1 sine of theta 1 is equal to n2 sine of theta 2. So we know everything except theta 2, so we'll solve for the sine of theta 2, so we get n1 over n2 times the sine of theta 1. And n1 is 1, n2 is 1.38. The sine of 23.1 degrees is something, they plug that into our calculator too. So we take the sine of 23.1, which is 0.392. We divide by 1.3938. And we should get a lower number because the angle is going to go lower, 2.84. So the sine of theta 2 is that. So we just have to take the inverse sine. So theta 2 is the inverse sine of 0.284. As long as we have it in the right mode, inverse sine of the answer in our calculator gives us 16.5 degrees. So the key things to remember here is the speed of light slows down as you go from a vacuum or from air usually into some other medium. That ratio of speeds is also the ratio of the index of refraction. And these are always greater than 1. Then you can use Snell's law, and you can solve for sine of theta 2, and then once you get sine of theta 2, you can take the inverse sine to find the angle. So just hold on, I will tell you if I'm right.
Recording started.
Okay, I've checked. We're good.
Recording started.
Now we're on problem number 13. So let's look at the problem. Page 754. Okay, so a ray of light is incident, which just means it's touching or shining, on the surface of a block of clear ice at an angle of 40 degrees with respect to the normal. So let's just draw that. So I'm going to make a block. And so we have our light ray coming in. And relative to the normal, which we'll draw right here, this angle is 40 degrees. So we'll call theta 1 there, theta 1 equals 40 degrees. Okay. Next thing. Part of the light is reflected and part of it is refracted. Find the angle between the reflected and refracted light. So the law of reflection is that the angle of incidence equals the angle of reflection. So we know this is theta. We'll call this theta 1 prime. So we know that theta 1 prime is 40 degrees. Therefore, we'll call this little angle here alpha. Because this is a right triangle, we know that alpha is equal to 50 degrees. Because 40 plus 50 have to equal 90. Okay, now some of it's refracted, which means it goes through here, but because the ice has a higher index of refraction, it's going to bend towards. And we can also extend this normal line in that direction. So this, we'll call this theta 2. And so we can use the law of refraction for the second part. And so what that says is that n1 sine of theta 1 is equal to n2 sine of theta 2, or that the sine of theta 2 is equal to n1 over n2 sine of theta 1. So we need to look up the index of refraction for ice, and I'm sure that's in the book. So let's see, ice, water, 1.309. So the index of refraction of air is close enough to 1, so that's all we're going to do. 3.09 for ice. sine of theta 1, and theta 1 was 40 degrees. So we get the sine of theta 2 is equal to, so we take the sine of 40 degrees, multiply it by 1, divided by 1.309. That gives us 0.491. We take the inverse sine. So the inverse sine of 0.491 is 29.4 degrees. So that's what this angle is here, 29. So this angle, we'll call this gamma, like that. So gamma is going to be equal to 90 minus theta 2. So 90 minus 29.4 is 60.6 degrees. So what we're looking for is the angle between the angle of reflection and the angle of refraction. So it's alpha. So what we're looking for is what we want to call it. We'll call it beta because we run out of. So beta is equal to alpha, or gamma plus alpha. Gamma plus alpha. And so we figured out that alpha was equal to 50 degrees from here. That's alpha. So I got in the wrong direction here. Gamma is what we just calculated. 60.6 plus alpha, which is 50 degrees. So the angle that we're looking for is 60.6 plus 50, which is 110.6 degrees. Okay, so hold on just a second. Let me check the answer. Make sure that's right.
Recording started.
So I've checked in. They had 111, which is 110.6, rounded off.
Recording started.
Okay, so I'm still got my cold, but we have to move on here. I don't want to finish up these physics problems. So this is problem number 17, chapter 22. And we did this in class, but just in case you didn't get that, we're looking at a beam of light that is bouncing off of two vertical surfaces. So let's just draw some vertical surfaces. So there's one. And we'll clone that. And then we have some light coming in, and it just gets by this corner, and it bounces off of there, and then it's going to bounce back. It'll keep bouncing back and forth as we go up. And the angle is 5 degrees. And this distance is 1.00 meters. So it's just a geometry problem. And this is 1 meter, the whole distance. So each time this thing bounces back, it's going to go twice this distance. So let's call this h. So h is going to be equal to something. Well, this is the opposite side of a right triangle. This is the adjacent side of a right triangle. So that is the tangent. So we can say the tangent of theta is equal to h over 1.0, which is the adjacent side. And therefore h is just equal to 1 times the tangent of theta, and that's the tangent of 5 degrees. So I have to make sure our calculator's in the correct mode, which it isn't because I was doing something else the other day. And so we just take the tangent of 5 degrees, and we get 0.0875 meters. So that's just that distance right there, 0.0875 meters. So the time for it to bounce off and come back here again is going to be 2 times that. So we can multiply that by 2, and we get 1.174. So every time this bounces off, we'll go 1.174. So the next time, we'll add 0.174 to that, and we get 0.348, and add again, and we'll get 0.522 plus 0.174, 0.696 plus 0.174. We get 0.87. If we add 0.174 again, we'll end up going outside. So that's going to be 1, 2, 3, 4, 5. So we'll bounce off the left-hand side, right-hand side 5 times. And we had the same kind of thing happen here, except we started 0.08, whatever it is, 875. So we could draw this in if we really wanted to. So this is going to go over here and then bounce back, go there, bounce back, there, bounce back, go there, bounce back, and it'll go there one more time, and then it'll go outside. And that's good because 0.87 plus 0.0875 is still less than 1, so we'll go in there. So you can figure it out just from 1, 2, 3, 4, 5, 6. So it's 6 times off the left-hand side. So we could just do it from drawing it to figure it out. So that's the answer. Okay, we're going to do problem 29. And what we have is we have white light coming in, and it goes from air into, let's see, water. And the index of refraction for water is different for red and blue colors. So what we get is one turns more than the other. And I'm not sure which way it goes. I don't know this well enough to just be able to say, oh, that means whatever. So we'll figure it out, and if it's wrong, we'll correct it. But these are the indexes of refraction. And because it's refraction, you use Snell's law, which basically says that N1 sine of theta 1 equals N2 sine of theta 2. And we're assuming N1 is equal to 1, even though air is not exactly equal to 1, but it's close enough given the accuracy of the other numbers. So if we want to solve for the sine of theta 2, it's going to be equal to N1 over N2 times the sine of theta 1, which this part is going to be constant for both cases. The thing that will change is N2. So let's open up the page, and so let's do the red color first. So the sine of theta 2 red is equal to 1.00 divided by the index of refraction times the sine of theta 1, which is 83 degrees. So the sine of the second angle is just going to be the sine of the first angle. Make sure I had the mode right. Yep, my calculator. So we have a sine of 83 divided by 1.331. And the angle should become smaller, and it does because the sine of the angle becomes smaller. So we get 0.7457. If you take the inverse sine of that, so you take the inverse sine and then you put the answer in there. So we get 48.22 degrees. So that's for red. And for blue, the only thing that changes is the index of refraction. We go 1.340 times the sine of 83 degrees. Sine of 83 divided by 1.340 is 0.7407. And if we take the inverse sine of that, we get 47.79. So let's see if I did that correctly, which I think I did. And the reason I thought this was that way because of our discussion on rainbows. But so what we see is that theta 1, or, what do we call this? Theta 2 red. Theta 2 red is 48.22, which is a little bit larger than theta 2 blue, which I don't want to use red there when he's blue. So that's theta 2 blue. Not a huge difference, but if you spread it over, the depth of the pool, I think we came up with class, it's a couple of centimeters. Okay, so that's it.
Recording started.
Okay, let's see, we got one more problem to do here in this section. And it's problem number 37, which is associated with internal reflection. So let's do this 37. A plastic light pipe has an index of refraction of 1.53. For total internal reflection, what is the minimum angle of incidence if the pipe is in air or water? Okay, so we've got two cases. We've got, let's call this N sub A, and we'll call this N sub B. And so if you have air, it's this, and if you have water, it is something else, which I need to look up. I think it's like 1.33. I'm not 100% sure. So we have liquid water, 1.333. If there's anything significant about that. Probably not. Okay. So all you have to do is you just have to find the critical angle, which is, there's an equation for that. And so I just have to find it. I'll just look at the summary section. Critical, yes, there we go. Total internal reflection. So it says the sine of theta is just N2 over N1. And N1 has to be greater than N2. So this is N1, and these are going to be N2. So all we have to do, so we'll do it for air. And so the sine of theta critical is N2, which is 1.00 divided by 1.53. So that's, what is it? 1 divided by 1.53, 0.653. 0.653, and so we take the inverse sine, so we do the inverse sine of 0.693, or 653, sorry. And we get 40.7 degrees. And so for water, the sine of theta critical is just 1 divided by 1.333. 1 divided by 1.333 is 0.75. And so you take the inverse sine of that, inverse sine of 0.75, and we get 48.6. And if you have something like, the higher the, actually, is that wrong? Oh, that's wrong. Hold on. Putting the wrong thing in here. I was going to explain that, but so 1.333 divided by 1.53. Okay, there we go. 1.3 divided by 1.53 is equal to 0.871. And the inverse sine of 0.871 is 60.6 degrees. thinking about this. Does this all make sense? As far as the angle being larger. Yes, okay, so let's think about this. Let's draw a picture. What we'd like to do is, okay, so here's my box. And here the light comes in. It's already inside, basically, and we're seeing if it'll escape. In the case of refraction, not even the case of reflection, we always draw it. The angle is always relative to the perpendicular to the surface. So this is theta sub c. And what we'd like to do is, what this is saying is that you kind of look at it from the other direction. We'd like to have as much room as possible in this direction to have internal reflection. And so when you have water, this angle is smaller, and so this angle is larger, so more of the light is going to remain trapped inside. Whereas if the water is the outside, then the angle is going to be like 60 degrees. And so only the angles between here and here, when the light is incident upon the surface, will be reflected internally. So ideally, if you wanted to have the maximum chance of the light rays remaining trapped in, you'd want to have low index of refraction here and as high as possible here, just like a diamond in air. And low is going to be air, okay? I guess that goes to show if you really want to keep optical fibers dry on the outside, because if you have a little drop of water here, then the signal could escape. And so low air is basically a vacuum, so it wouldn't really help you a whole lot by putting it in a vacuum. And then the material that you'd use for the fiber optic, you want to be as high as possible. Of course, we can't use diamonds, so use something that's, whatever the most cost-effective way it is to give the maximum internal reflection.